everyone, how are... Oh my gosh, that was... Oh, it's still connected to my phone. That's why I heard that loud boop. Let me get this disconnected. Okay, so that's what's happening here. I can get this disconnected from my phone and reconnected to my computer here. Is anyone in the chat? We'll wake up Mubot here. I heard the boop because I'm doing the two-factor. Try to get this connected and not connected to my AirPods. Connected to my phone. That's why we don't hear anything on the stream. But now we're connected in, it looks like. Now we're getting AirPods started up on the computer, not the phone. Connecting. Connecting. Still connecting. I heard the noise. Should be connected in. AirPods connected, it says, and do we hear it? Ew, we're connected. Good to see everyone here. If people are here, are going to send out a link to 201. Let me say, office hours live. Send out to 2072. Click here. I even do a full regression review and talk about the test. That'd be really good, right? Do that. Office hours. Might be a chill day. Margaret, good to see you. What questions do you have? Drop those questions in the chat. Little bit sniffly, little die. Any questions you got, drop them in the chat. Excuse me. Chat. I hear myself cough. Oh, that was... Hey, Jennifer, good to see you. Yeah, cool. I feel like I'm fading. Oh, this shirt I think makes me fade away more. Like, see my hands? Man. Ow. I don't know what it is about this shirt. You know what we could do? We try to do something crazy really quick. We've got new lights. Got new lights right here. I wonder what would happen if I try to set up some new lights. There's my hair. All right, let's see right here. Let's try this. Let's open up this box. This is an unboxing stream. So we're doing an unboxing stream. Here's the box. New lights. Unboxing stream. All right, we're gonna open up this box and see if how hard it is to set up these new lights. Because this might fix some of the situation. A little bit of work right here. Oh, ooh, it's in a fancy case. Unboxing stream. Oh, does it have a handle? Oh my gosh. He's an influencer now. We're doing the unboxing stream. Here it is. Here's the thing. Oh, see, we got a handle. Great video maker. What we got right here. Good morning, Joe. Good to see you there. Catalina, thank you so much. Let's throw 100 points. Okay, we got great video maker. Okay. We're opening it up. What we got in here? Unboxing stream. We'll get serious here in a moment. We'll see if we can do this in 5-10 minutes tops. Be better if I had like a camera. If I could do this easier. Okay, looking good, looking good. Whoop. Okay. What we got here? Good morning, Blakely. Feels like it's not hurt. Look at this, great video maker. Okay. Ooh. Oh my gosh, look at this. It's an LED. LED lights. It's got a shutter on it. It's got shutters so you can like close them off. Please remove the protective cover before use. There, I did it. I removed the protective cover. Okay, we got one. Shouldn't be too hard to set these up. Should just be plug in. Just be plug in. I've used lights before. It's got some sort of things. Got the gel pack to keep it so fancy. I know, right? It's got instructions, disclaimers. Please read the instructions carefully and use the product carefully. If you don't obey the instruction warning, you may cause harm to yourself and people around you, even damage the product and other things. Security injury. Okay. Instructions. If you have questions, let me know. Product analysis. Okay. Installation mode. Screw in the thing into the thing. I've done that before. Lamp can be installed. Turn it clockwise. Insert the diffuser from the side panel. So insert it Loosen the knobs, both sides of the U bracket, just the panel, then tighten the adjustment on the knobs on the U bracket. There are 2 power supply modes to choose. So connect the power cord and adapter to the power supply, purchase 2 additional lithium batteries and use them to power. Okay, so connect the power cord. Okay, we're going to connect the power cord in. So we're not using the battery slot, we're using the adapter interface, which we should have. Lighting control, fondle can control the angle of light. And so align the mounts and then open, do you manually open the shutters? Line the front mount holes with the screw holes of the hinges and lock the latches with screws. I'm supposed to add screws this? And then there's external soft lighting, purchased separately. I didn't purchase that. And it's got a bunch of keys. Didn't see any warnings on here that I'm going to cause problems. Okay, so that's the back of it right here. Okay, we got one of those. And then let me grab the other one. I'm doing a little unbox stream here before spring break. And so we got the other. We're going to have better lighting here. Oh my gosh. Okay, so here we go. Please remove the cover because they're probably making sure the knobs and dials don't get hurt. Cool back interface. There we go. Both of these. Got to do the 2-point lighting. Then I can give Terry back his light and we can see if we have better lighting. Okay. What is this? Box right here. This looks like wires. It looks like the adapter cords. Yeah, let's do canvas content right after this. You bet. There we go. We got 2 AC adapters. AC adapter is going to plug into those. And so we'll toss out that box. And then we've got the rods right here. We'll do canvas content right after this. So unboxing stream, then canvas content. So here we are with the stand for it. And it's got a multi-mount, or you need to increase this. Ow. Increase this, turn this down. Looking good. Legs come out. Didn't tighten one of the things down. How's everyone doing this morning? Is anyone doing anything exciting for spring break? Any exciting spring break stuff going on? I should have unloosened this. No spring break things? Surely someone's going somewhere for spring break. Anywhere? Anywhere spring break? Catching a flight to Fort Myers. Cool. Why is it not doing that? I've worked with 1 billion of these. Literally 1 billion. Oh, there we go. Is that enough? Wait, there we go. That's probably good. Probably good? Okay, so this it probably has to go higher is the problem. There we go. Sometimes they like come out of their slot when you do it. We're almost done with the unboxing stream. I'm gonna stand up nice. Looks to stand up nice. Ooh, these are good. This is gonna work out really well. And then I need the proper plugs for these. Okay, we got 1 stand set up over here. 1 stand set up. We're doing canvas content right after this unboxing stream. And second stand needs to get set up now. Going to Alabama. I drove through Alabama. Alabama's nice. My worst class got canceled, so I'm thrilled. Nice. Your worst class. We didn't cancel Stat 201. Chapter 8 quiz. Yeah, which question's on it? We'll do canvas content, then we'll do that. We'll do canvas content, and then we will do chapter 8 quiz after this unboxing stream. Hey, Jesse, good to see you here. We're doing an unboxing stream for the moment. Got cool new things. Got cool lighting arrangements. Cool lighting. I'm doing it because this t-shirt makes the chroma key go bad. You can see it, like it starts to register incorrectly on me. There, my hand just did it. You have to watch really carefully, but the t-shirt for some reason, you see my shoulder right there, if you look at that, or my bicep, whatever, that's on my shoulder. I don't know anatomy. it makes it go bad. And so I'm frustrated by that. And I have this new lighting, and the new lighting should illuminate me better. And if it illuminates me better, I need to not hit that. That would be very bad if I broke something up there. If it illuminates me better there. Oh, wow, this one's a lot better now. Okay, let's do this. Okay, I need to work with that other one now. Don't hit things, Brian. Don't do it. Don't break things. Can't break anything at UT. Don't do it. So, yay! I think it's pretty cool. Okay, this is gonna be pretty good right here. This one, pretty good. We go right here. Okay, so now maybe I put it right here and block that. This you'll report one in the fastest cyclist, you bet. I think it's like times of fastest cyclists over years. That's a really high one now. Okay. Ooh, we're almost there. You see, that's part of the problem. If you look at the green screen right now, the green screen is losing part of its thing, which we don't want. We want it to not have that issue where it's showing that. Well, that's the diffuser. It's already in there. It told me to read all the instructions, and then the instructions are not really that informative. They're just like, do what you normally do with lighting gear. So it's like, oh, set it up like you've done a billion times. Funny, I never thought as a teacher I'd be like doing lighting and stuff like that. Read the instructions. What else supposed to do? Okay, that's got that. Diffusers are open. We are one step away. We just need to plug in now. And this one needs to bring this down a little more, I think. A little wobbly. There we go, like that. We're almost here. Okay. Okay, we've got, that's gonna stay up really well. Okay, we're almost done. Chapter 8, you bet, Grace. We're gonna do it here in 1 second. We're doing an unboxing stream. I wanna see if people can tell the difference right here. Unboxing stream almost over. All I have to do is plug in the power cords now, and we will have completed our great video maker lighting. We'll see if it looks any better. All this work right here for lighting, almost done. Unboxing the power cords right now. So are the lights not blinding you? They can be really blinding. Has anyone ever done any like studio or filming? The bright lights in your eyes can be really, you have them off to the side. So I should take a picture of my office. I should clean it up a little more too. But you have them off to the side usually. They're not in front of you. So they illuminate. So when I turn these on, hopefully the green screen stops doing that wrong color key or whatever at the top. If you look at the top of the green screen, it's acting kind of funny right now because it's having trouble with that area due to the green screen not being completely one color. So you want your green screen to be all one color. And so now, first light coming on right here. And that's all right. There we go. First light turning on. There we go. Whoa, no, not even. Well, look at this, look at this. When I turn the first light on, watch that. Do you see it? No joke. Like watch again. There's light off. You see it at the top? And there's light on. Just instantly with one light. Instantly, and we'll do some fine tuning adjustments. But that did it right there. Now we've got shadows. Okay, now we got a lot of shadows. And it is very bright. Okay, now we got a lot of shadows. We need to turn this way. Not being properly illuminated. Thank you very much. Yeah, the lighting is a lot of work. Lighting is there some help on chapter 8 quiz? Yep. I don't think we did chapter 8 quiz yet. We're just doing an unboxing stream for the current moment. I'm gonna try and make this better, and then I'll do some adjustments over spring break. As you can tell, this takes a moment right here. Thank you, everyone. This will be in the video. I guess we'll do this unboxing. Hey, I'm right here in front of you. But proper lighting is a big task. It's not a easy one to get good lighting. For anyone who's ever done video stuff before, it takes a lot of work to get everything perfect. And then there is no perfect. There's only better lighting. There's only better and worse lighting. You can have really bad lighting, and so you got to be like, okay, how do we improve the lighting? Okay, I got one more plugin back here. Hopefully this removes the shadows because we got 2-point lighting now. We actually got 3-point lighting, but might have to remove my iPod charger. Oh, no, I got it. And I gotta remove that. Okay, gotta find a new spot for this. Oh, there we go. Okay, got too many things. Don't want to have problems here. Okay. Okay, 2-point lighting happening in a second. There's that. I think it's better, isn't it? I mean, it's really bright. Let me adjust this really quick. We need to bring this down. That's this side of the face. All right, we need to bring this down a little bit here, and then we'll be better. Okay, intensity. We're gonna bring down the intensity. There we go. Intensity down, and then this is the, like the blue. We're gonna go low blue there. We're gonna bring down the intensity on the other one a bit. Intensity down, and then a little more blue. And I think we're good. I think we've done it. See, now I'm a little dimmer on this side. Bring up the intensity over here. One. There we go. Okay. It's showing that it's this side. Need Jason here. Jason, where's I'm a tech guy, man. Okay, I think that's got it. If I could, what do you think? Better or worse? What do you think of what do you think of the lighting quality? Better, worse, what? And actually, if I turn this off, because that's multiple lights. See, right there, that's the lighting. So this one over here is too bright. This has got it. This is quite the illuminating stream. Okay, I think this does it. Yeah, there we go. And now we shouldn't have, I think it's a lot better. If you notice, I think we still got it right there. It just did it. I'm trying to do it. It was a little, yeah, it was. And now it should be better, and I should be properly illuminated from the proper angles, and the green screen should be illuminated. So, and hopefully I'm casting no shadows on it, because we got the, I can see a little bit of shadow, especially right there. You can't see it, but you don't want shadows on your green screen. You want an even green screen. I'll take a look at the stream later. But yeah, well, it's got it. Well, professional lighting now in the office. Good to go. Let's do some Canvas content. Thank you everyone for hanging out while I did this right here. But so you can see as I go a little further back. But I think, yeah, it's more natural skin colors. It's what you want. So gotta have that professional lighting. Okay, let's go here to the Canvas content. I gotta get used to it now, because when I look that way, I might even maneuver that more over there, so that way it's not directly in my face, because okay. I gotta do it. I gotta move it, because as I'm looking over there, I'm seeing it. Okay. Because someone was like, is it gonna blind you? And I'm like, it could. Okay, that's better. And it looks good. Okay. Let's do, who wants to do Canvas content here? We're gonna do the Canvas content. Canvas content coming right up right here. Canvas content due next week, but let's do it now. Put it in the stream right here. Did I lose everybody? Hopefully people are still here. You're welcome, Grace, and thank you everyone for hanging out while we did this little unboxing stream. It was just on my mind, and I was like, well, you know, if I do it right now, it'll get done. And then I can actually view it, and people can give their comments, be like, that's horrible! Worst lighting ever! Okay. Over to the main screen. Okay, let's put it in the video right here, the Canvas content. I think it looks better, right? It should be more popping off the screen. I should have better skin tones. If we do better lighting, everything just looks better and more realistic. So take a look at previous videos, but I think this lighting is helping out a lot. I have to take a look at it later and see how I evaluate it. So with this, see if I go forward, I go into the, there's no light up there. Got to hang out back here. Okay, enough about that. Let's go to the 23-minute mark, Canvas content regression. Okay, so with this Canvas content, we're going to take a look how to do it right here and answer the questions. Adding together all the residuals in the plot will sum to 0 on average. So what is a residual? Thank you, Catalina. I do love doing it. It is a lot of fun. What is a residual? What is a residual? And the reason I think I love doing it is because I've constructed a lot of what I have. So I have had help, but I'd say 80% of it's been my work. But the 20% I needed the help with. So thank you to everyone. Great job right there, Joe. It's the actual minus the predicted. So the prediction comes from the line, which would be the y hat. So anything on a line is a y hat, solved from y hat equals b0 plus b1x. And then over here, you have the dots, which are the actuals, which are going to be the dots like this right here. Now, the line itself minimizes the sums of squared error. That's a Canvas question or a My Pearson question. But a residual is actual, which is the dot, minus the predicted, and that is equal to the quantity of E. And they will be sum above, sum below, sum above, sum below. And if you were to take the sum of all the residuals, they would sum to 0. The some are negative, some are positive. And that is a fact right there, that if you add them all up, they kind of squish around the line. So yes, the sum of all the residuals is 0. It's just a fact. That's you can write it down, you can memorize it, but then also try to understand conceptually that the line goes through the middle of the data. So if you drew a really small model like this, you could see that if this was like -2 and this was -3 and this was +2, what would the last residual be? So think about this concept right here. If this is the theoretical line and this one is -3 and this one is -2 and this one is +2 and this is +3 theoretically, oh, I just said it. You see what I'm doing right there? Is that last residual has to sum to 0 because -3 plus +3, it's not like they're always opposite of each other, but if you were to sum up all the residuals, then +3 plus -3 is 0, and +2 plus -2 is 0. It gets more complicated when there's a lot of points, but they would kind of smush around the line and sum to 0. So the line goes through the middle of the points, minimizing the sum of squared error. If the correlation coefficient is 0.5, what is R squared? So what in notation is correlation coefficient? You should know the notation for correlation coefficient. Correlation coefficient in notation is what? Correlation coefficient in notation is what? Correlation coefficient in notation is what? You should know this. It's R. Yep, that's what correlation is. I don't know why I chose R, but it's part of the, I guess it's part of the word. So if it's telling you that the correlation coefficient is this, well, then we're asking what is R squared? Remember, R squared is percent of variation in Y explained by the variation in X. So R is equal to this. So R squared is equal to 0.5 squared equal to 0.25, because you just square 0.5. Now, be careful, though. When you want to find correlation from R squared, you need to do a two-step process. Catalina, great job right there. The two-step process, and write it down to remember it, to find R from R squared is to square root it and then check the direction. Because when you square root it, you get like a positive negative. You don't know which way it goes. So when you go from R to R squared, you just square it. But when you go from R squared to R, you square root it, and then you look to see the direction via the slope or the direction of the scatter plot. Very important right there. If the residual is this and the observed is this, what was the predicted value? Now I can solve this super quickly. There we go. So how did I know that? Well, this goes to the idea of what is a residual and when is it positive. I swear there's a test question that asks, if the residual is positive, what does that mean? So let's think. If a residual is positive, which this one is, what do we know? When is a residual positive? Those are all the y hats. When is a residual positive? When is a residual positive? When is a residual positive? So in our class, we talk about the line, and then we talk about the positive and negative region of residuals where the dots are. So when is a residual positive? Can you explain to me, and this is a good note to have, can you explain to me when is a residual positive? If kind of, and Joe, you are correct. And I always like to say it's positive when the actual is higher than the predicted. And Catalina has right there, when the observed is higher than the predicted. Observed and actual are synonymous words. Like this right here is where, we'll do it in a light green. This is where the actual is. This can be called the actual or the observed, and it's the value of y. Does that make sense? That's the actual point. That is the observed. And so a residual is positive when the what is what to what. So repeat it, take a note of it. A residual will be positive when the what is what to what. Try to write the full sentence. A residual will be positive when the what is what to what. So the full sentence, try doing it as a full sentence. The residual will be positive if the what. So I mean, it's right when the dot's up here, right? So this is the line, this is the dot. So the residual will be positive when the what? And observed is just another name for, I'll highlight this right here. Both of these are the same name. When the observed value is greater than the predicted, exactly. So we know, so what should we do here to get the predicted? And you could go through and solve the math equation, but just think theoretically, if you know that the residual here is 1.8, you know that the predicted, or the actual, excuse me, we know the actual value. So think what you can solve the equation, or you can see it theoretically. Like by drawing it out, you can see the answer, and this is how I did it in my head. So there is what I was looking at in my head when I was thinking through it, and there's the information we have. We are trying to figure out the predicted, and then I'm going to plug the equations in. We don't know what this point on the line is. We don't know what that is. But we know the distance it is away. We know the observed. And so you go down here and you say 1.8 equals, and then we put in the 20.6, and then we go here and do the minus x. So we don't know what x is. That's what we're trying to find. But think, we're just going to subtract from it, right? So if you do this, you can bring 20 to the other side by subtracting from both sides and get negative 18.8 equals negative x. Now you times by 1 and get 18.8. And you can check your work by plugging 18.8 in here and asking, is the difference between 18.8 and 20.6 1.8, which is the residual? Does that make sense? And then you want to interpret it to say like, oh, the actual is 1.8 higher than the predicted. How does this make sense, Catalina? And then try working through this right here, understanding the terminology. So this is the key to getting these problems right, is to understand what the questions are asking for. What are they asking for? What does actual mean? What does predicted mean? What does observed mean? What does residual mean? And then being able to do like a small drawing like I did right here, where we can plot the numbers and say, okay, the actual is 1.8 higher than the predicted, and then we can solve the math. If you can do it theoretically and you can do the math, you're good. What are the two steps? Step number 1 to finding r from r squared. Don't read their answers. 2 steps, r from r squared. First, find the what of it. You're going to find r squared from r. So when you go and you have r squared and you want to find r, you got it right there, Joe. Because think about this. What is the correlation of this? If we know r squared is equal to 0.81, what is the value of correlation? And you have just done it. Catalina's doing it right there. So go ahead right here and find the value of correlation for this. R squared is 0.81. Try typing it in your calculator to see if you can do it. And you'll see you're doing it. You are doing the steps you just told me to do. So r squared is 0.81. So you need to square root it to get r. And then do the next step. Catalina, be careful though. We're throwing 100 points. We haven't thrown out points lately. Be careful, Catalina. It's not 0.9 though. It's not 0.9. Correct it, get some more points. It's not 0.9. Not 0.9. Negative 0.9. And that's the second step people usually forget. And that's where you have to look at the direction. How would you know if it's positive or negative? You have to look at the direction right here and say, oh, it goes down. So then it's negative direction, negative 0.9. That's what the mistake people usually make. You have to then confirm, because when you square root something, you don't know if what you squared was positive or negative. So yes, we need to square root it and check the direction. So take the square root, check the direction, the scatter plot or the slope. For each 1 unit, if you get this on your test, you have literally just been given a interpretation of the what. This is a present to you. You have literally been given the interpretation of the what. If you see this test question, take your scratch sheet of paper and write it down. Like, if you see a test question, write this down. This is the slope. And then when you're doing your interpretation, you just put in the X right there, you put in the Y, you put in the B1 value, and you maybe mention what a 1 unit increase is. You just got the interpretation of the slope for free. That is happy day right there. Man, if I got that, I'd be like, what did I get wrong? What did I do? Square, oh, I said square. Oops, square root it. We said that. I was like, what did I do wrong? Take the square root of r squared. Do not square r squared. Just so you can know, someone's gonna be like, he doesn't know how to do this. Just so you can see, I was talking about square rooting it. I swear, rewind the video, I said square root. But then I clicked the square button. Square root your r squared. Don't square your r squared. Then you get r to the fourth, which I don't even know what r to the fourth is. It's a weird quantity we statisticians don't use, or business analytics people. That's the problem. I'm not business analytics. I got that one wrong on my first try. No, Joe, did you get 100 on your second try? Did you get 100? You got this. You got this. If you got it wrong because of me, let me know. If you got it wrong because of me, let me know, because then that's not fair. If you were following along, you saw me click that, and you're like, well, I thought he said this, but he clicked this. So, I mean, he should do, Brian knows what he's doing. Predict the value. You got, okay, Joe, message me and we'll fix it. We'll fix it. My fault, you shouldn't lose points. You can do your second try here too with us if you want, but let me know if your fix didn't work. Do the problem, tells you to predict the value. Yeah, let's try that one. We'll find it. We'll do 2 more versions probably, and then we'll do some chapter 8. I can tell all the residuals sum to 0. Very true. It's a fact. This one asks you to find values in the output. So the r squared, oh, nice job, Joe, right there. Keep up the good work. R squared is the value right here. Now, when you interpret r squared, I want you to try this. We'll throw out some 100 points if you get it. You do what with the value of r squared? So what would we do with this value of r squared when interpreting it? You could get output just like this on the test. Hint, hint, hint. And you might have to interpret the r squared. So what do we do with the value of r squared on the test? What do we do with the value of r squared? What do you do with the value of r squared? When you interpret it, you do what with it? What do you do with the value of r squared? You take the r squared and you do what with it? So r squared is multiplied by 100, bingo. It's going to be a percent of variation in y explained by the variation in x. So 34% or 34.4% of the variation in finish times is explained by the variation in age of the runner. Does that make sense? 34.4% of the variation in finish time is explained by the variation in age of runner. Blank percent of the variation in y is explained by the variation in x. Have that written down. Check out the review videos where we do those. You should have it. So, man, look, and if you get this on the test, you've now gotten a r squared interpretation. I mean, I think we even put this on the test sometimes, like, I'm zoomed in. Man, if you get that, that's an r squared interpretation right there for you. 34.4% of the variation in phase time is associated with the variation is explained by, that's fine. Same thing. You can say associated, explained by. I like explained by. Slope right here, this is going to be for each 1 unit increase in x. We expect y to increase by b1. The slope of a model, make sure to know where that is at in the output. Slope is what in notation? Slope is what in notation? What is the notation for the slope? Given hints on the screen right now. What is the notation for the slope? What is the notation for the slope? What is the notation for the slope? The notation for it, B1. For each 1 unit increase, B1. So this is it right here. It's 2.43, and the intercept is 156. So 2.43, and the intercept is 156. I think it's got it. For each 1 unit increase to next, we expect y to increase by or decrease if negative, slope. Now here we go with find the predicted value. So with this right here, with find the predicted value, we need to write our, think of the E word. We need to write our what? When it says find the predicted value right here, we need to write, what E word am I looking you to say? Because how do we solve this? We need, yep, equation, you got it. Great job, Catalina, 100 points in the chat. So with this right here, we write y hat predicted y value equals to b0 plus b1x. And we go here, and the value of y hat is going to equal b0, which is 11, plus 3 times x. X is equal to 6. Plug the x in here, which will give us the value. I'm going to write it up top now. The value is 11 plus 3 times 6, which is equal to 11 plus 18 equals to 29. No. Does that make sense right there? Just plug in the values of b0 and b1, know where they go in the equation, and you should have it. And it was 29, was it? I'll double check my work. But the value is 29. Go. If a residual is positive, what was larger? We did the homework. We did the homework, I think, last office hours. So we'll probably do some of the quizzes here, but we've done the full homework. Full homework is done. If a residual is positive, which was larger? Anyone know? Residuals only deal with two concepts here, so there's only two possible answers. So you got a 50-50 shot if you know what residuals deal with. So when we find a residual, and you get the formula on the test, I think that's right. Yep, that is correct, because the dot would be higher, right? The dot's gonna be up here. So I think about it conceptually. Yeah, well, the 50-50 shot. Remember, the residual formula is actual minus predicted. Actual minus predicted. Residual equals actual minus predicted. Another name for the actual is the observed. It's just, there's multiple ways to call it, but that is the observed. This is also the value of y, and this is the value of y hat. And so we have right here that the residual E is equal to y minus y hat. And the way this looks is if you have a prediction line, the positive residual zone is up here and the negative is here. So a dot above the line is where the actual is at, and the line is the prediction. So the dot is above the prediction. Does that make sense? So the actual or the observed point. And then always, if you've been practicing, hold your arm up like this and then put a dot here. This is the actual. My pen right here is the actual, and this is the prediction line. So by doing this right here, you're saying the actual point is higher than the predicted positive residual zone. So, and slope and intercept have nothing to do with residual. I mean, they're part of the equation of the line. They don't have anything to do with the calculation of a residual. Yay, finally 10 out of 10. Let's do one more version, see if we get new questions right here. Okay, I got to do a preview. I want one more 10 out of 10. One more. Adding together residuals will sum to 0. Very true. If the correlation is this, what is the r squared equal to? Square correlation to get r squared. This is the slope interpretation. If the residual is this and the observed is this, what is the predicted value? It means we were that much higher than the predicted, because remember we just said a positive residual means that the actual is higher than the predicted. Jump output, r squared is the variation, slope is the value of 2.4. We just did this one, going from memory, should be good. Try one more version, that was too easy. Let's do another one. And here we go, one more version, see if we get new questions. Same jump output we've been doing, r squared is the percent variation y, explained by the variation x. Slope is b1, even tells you that. And the intercept is b0, seen from the regression output right here, b1, b0, and r squared times by 100. This is the slope interpretation. Solve for the equation. 7 times 3 is 21. 21 plus 12 is 33. Adding together residuals will sum to 0, very true. And you square r squared, or you square r to get r squared. Well, darn it. I think that's it for the questions. You know, you really get down to where you kind of know them verbatim. Like, oh my gosh, I love this question. This is a great one for us to finish this last round of questions on. If the residual is 0 and the observed is this, the negative 2.8, it's probably one of these versions right here. So for these questions, you need to write out the equation. Blakely, each version of the question is different. So for this question, you need to write out the equation. And Joe's got it right there. You need to mark your notation, as we always say here, and I met Leo.
Notation,
brother. So residual should be marked as what? What will residual be marked as? In notation, residual will be marked as what? This is the easiest version to get of this question. What do I mark residual as in notation? In notation, like what notation will I use for it? There's two possible, but traditionally we should use something. Points in the chat, E. And then observed is the y value and predicted is the y hat. So now we write out the equation that residual equals actual minus predicted. and we don't know what the predicted is, so we say 0 equals 19.2, which is the actual, minus x. And then you can see right here when you solve it, you get 19.2. Because like, what is 19.2 minus 19.2? It's 0. But then if you algebra it out, does that make sense, Blakely? So try solving these out, and then also try drawing them out. This would be that the point is exactly on the line. That's the only way to get a residual of 0. Negative would mean that the what? Finish my sentence. A negative residual means that the what is higher than the what. A negative residual means that the what is higher than the what. So a negative residual. When residuals are negative, like this one down here, the predicted is greater than the actual, because the prediction would be up here and the actual would be down here. So that's the way it's going to look. So whatever the distance is, you would want to add it to the actual to get the predicted, or subtract it in the positive sense. And then you should be able to mathematically see that. Try drawing it out. The predicted, and yeah, Catalina, really good work, Catalina and Joe. Is it making more sense? Just the more you do it, if the residual is negative, you're down here. Doesn't matter if the slope is positive or negative, but a negative residual indicates that the actual is lower than the predicted. You're lower than the line of prediction, the negative residual zone. Positive residual zone, actuals are higher. So just always try to do that and be like, wait a minute, what's a positive residual mean? Oh, it's up here. Just remember, you move this hand above the line. And you can just think positive residual zone, negative residual zone of 0. Practice. That's, we got to memorize the concepts. Yeah. Thank you so much, Catalina. It is a tougher chapter, but you start to get it down, and then it's just repeating the concepts. Everything is repetition. The more you solve them, the faster they get. You get to the test, and you're like, this is not so bad. If a residual is positive, which is larger, the actual, the dot is above. Thank you so much. And correlation right here, square it to get r squared. And you can sum them up to get 0. Okay, let's do some Pearson. We got new lights, new stuff. Even my t-shirt can't make me fade away now. I'm fading away. Da, 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 da. Whee. Okay, so we had the cyclist question and something else. The cyclist and something else. I can't remember what the other questions were. Oh, we have a Mario Kart event today in the atrium of the Haslam Business Building. So check out Mario Kart today. Going to be a lot of fun and really excited. Play some Mario Kart. Hopefully no one beats me. Hopefully. I've been beat before. There was a student last semester who like played in tournaments and stuff. He would run the tournaments at like a game place, and he was like, yeah, people used to come in and think they were good, and I ran the tournaments and I would just destroy them. And I was like, haha, I'll take you on. He destroyed me. Yeah, he was really good. Shouts to him right there. I was like, okay. He's like, you don't have every card unlocked? And I was like, sorry. Okay, Tour de France. I think we found the cyclist one already. It's a bit of a weird one. Bit of a weird question. So this is Stat 201, Chapter 8, 100 years ago. 100 years ago. Okay, with this question right here, we are first given scatterplots, which is the visualization of two quantitative variables. We're also given all the data. Now, what you want to do is you want to take the data by clicking here, then click the copy to clipboard button. Once you've copied to clipboard, hit Control-C or Command-C on your Mac or PC. Now that you have it copied, go into Jump, and inside of Jump, go to File, New, Data Table. File, we'll bring it towards the center screen. File, New, Data Table. File, New, Data Table. With File, New, Data Table, don't click inside of it. Go to Edit, Paste with column names, because there was column names. So now that we have pasted with column names, we get the data, and we're going to start the analysis. Now, it hasn't told us what to analyze, but we only have two quantitative variables here, and we're doing regression. And do you think we want to predict what year it is, y variable of interest, or predict the average speed the cyclists were going? What makes more sense to predict? Like the thing we want to understand. Do we want to understand what year is it? Or what speed were the cyclists going in the Tour de France? Speed or year? What makes more sense to predict the y variable of interest, the response that we want to talk about? That's why we call it response, the thing we want to talk about. The speed of the cyclists. So we're going to go here to analyze fit y by x. Great job right there in the chat. Analyze fit y by x. The y variable of interest will be speed. So we'll go right here and we'll say, well, maybe the year explains why there is a certain speed. So maybe year explains why there is a certain speed. Let's go ahead and click OK. From here, we get the plot. There's some gaps right here due to the world wars, World War I, World War II, in the 20s and in the 40s. So that's why that data is missing, and the plot, the question will mention that. Next, we go here to the red arrow, click the red arrow and go to fit line to fit the regression line. Boop. Now we get the regression equation. I'm going to make it smaller right here. This is the y variable, predicted speed is equal to the intercept, and we'll bring it down to 2 decimals just in case it says 2 decimals. Make sure to put the negative in. And then, oh, it might say 3 decimals. Well, I'll say 3 decimals. Some of them say 3. And there's the regression equation. Y hat equals b0 plus b1x. You can also see it down here, lower on the screen. There's the estimate of the intercept and the estimate of the slope, and the statistical significance of the model is the significance of the slope. Write that down. The statistical significance of the model is the significance of the slope. And yes, you can also see some fun math tricks, like 29.06 squared is about 844. Oops, I didn't square it. How in the world did I know that? Well, that's because the F ratio is the t squared of the slope. Slope is the significance of the model, like this, the analysis variance. Not in 201, but just fun facts with Brian. Fun facts about statistics with Brian. There we go. So let's talk about your question now and what it wants us to analyze with this regression model. First off, I want to point out there seems to be a pretty big problem here with this regression. And I see it not so much there. What is the problem I see? And be very careful. This one gets a little tricky with the way they want you to word this, but I see a problem down here. What are our conditions for regression? Think through them and think about what problem I see right there. Trying to like give audio cues. What is the problem we see right there? You have to think through the conditions. Q. No outliers. Plot doesn't thicken. There's a bit of a problem. QQ straight enough, no outliers, plot doesn't thicken. It has a bend at the start of it. It goes. The fanning out, yeah, there might be some fanning out. And here's another test question. We like to do test questions here. The best way to analyze the plot doesn't thicken is to make a what? I'll give you a hint on the screen. The best way to analyze the plot doesn't thicken is to make a what? The best way to analyze the plot doesn't thicken is to make a what? Best way to analyze the plot doesn't thicken is to make a what? Residual plot. And yeah, there's a little bit. You can really see the bendy nature of it. A residual plot is a plot of all your residuals called a diagnostic plot to diagnose issues. And I do see actually it gets thicker in here. That's where the thickening is happening in here. It's stronger in here, stronger in there, and a little bit of thickening in there. And I wish Jump, I don't know if Jump has an equal spread test on it. They should. Oh, we don't have repeated, so there's issues. I could do this in R probably better. So let's go ahead and look at the questions they ask. And first they want the graphic of it. And going from memory, it looks more like D. And let's double check. It should go to the low 50s. You see how this goes? Or it goes right up to 50. If it's this one, it's going to go to 40. And if it's this one, it's going to go to 40 also. So, and that has a weird gap at the end that we don't usually see. Let's go look at the data again. It goes to the 40s, and then it has nothing weird at the end. Wait a minute. Oh, here it is. It's going to be this one. It doesn't have these weird points. You see these weird points right there? Like those points right there? We don't have those points. So since we don't have those weird points at the end, and I'm talking about this over here, there's no weird points. It is this one. It also goes to the 40s, confirming. It goes right to there. I wish they didn't extend the graph to the 50s, but there's no weird points at the end like these, and it doesn't go up to nearly 50, and that one has weird points too behind my head. So yes, it does ask the equation, and it says to 2 decimals, so the equation is listed right here. Do not forget the negative. Do not forget the negative. If you forget the negative, I'm not going to give points back. Why? Because, oh wait, yeah, negative intercept. I was like, negative slope. The negative is super important. It's a huge difference. It's a small error, but it's an error. The relationship is positive. There's a nonlinear 10. So we have to choose. Excuse me. This is where I'm between B and D. I don't think there's a large amount of scatter. That's where I don't think there's a large amount. Large amount of scatter is talking about this, like the vertical scatter. I don't think there's a large amount of scatter. I think there's moderate. And there's small problems with linearity at the start. And they're saying general linear. They're not saying it's super linear. They're saying it's a little bit linear. So that's where I get a little bit, I don't like their words. So this is where it's not straight enough in the early part, which is what we mentioned. And there's no real outliers. We should, whoops, cancel. I want to check the question. 80 was the bottom one. The variables, oh, because they're saying the relationship is not, oh, are the conditions met? I thought, are they not met? Is there a problem? Sorry. I read this. So no, it's not straight enough in the early part. There it is. So it's not going to be met. Sorry. Yeah, I misread it at the end right there, where it says, are they met? I thought it said, are they not met? And I was thinking, yes, there's issues. So literally, I just chose between the answer that, yes, there are issues. And I was saying how there's a straight enough issue. So this one always gets me a little bit because they're basically pointing out at the end that there are issues. But it's that you should fit a higher order polynomial through this, which is not hard to do. Probably like we could look at a second or third degree polynomial. And this is what we would do. Probably let's go up here to fourth degree polynomial. Sure. And then the R squared adjusted here is 0.8888. And then that one's 0.89, so a little bit better. And this one's 0.915. Maybe some overfitting. I don't know. Those are topics for another day. But R squared adjusted went up. So I'm going to go with that. Residuals actually look good. That's nice. So with this right here, pretty good question. Knowing B0 and B1 is probably some of the most important parts of this. Interpreting B0 and B1 is something I wish this question had. Like for each additional year since, well, for each additional year, we expect the speed of the cyclist to increase by 0.14 on average. At year 0, which is not interpretable, we expect the average speed of a cyclist to be negative 247.90. This is illogical because people weren't doing the Tour de France in year 0. So that's a huge extrapolation well beyond the lower bound of the model. So that would be not interpretable intercept. Let's keep doing questions right here. Pretty good question, which it asked for the R squared interpretation 2, which would be, and I hope people are watching this because this is some of the important stuff you'll get wrong in the test. R squared would be 88.9% of the variation in average speed of the cyclist is explained by the variation in year. Blank percent of the variation in Y is explained by the variation in X. Know how to interpret it. You will write it out on the test. I think we did this one. What other questions do people have? It is open questions. See if I find the other questions. What other questions? There was one other one. So once it's cyclist and another one. Institutional report. Institutional report. Got more questions though, because it's open question time. Oh, there it is. Institutional report. Okay. Institutional report question. Not spring break yet. In institutional. All right. Awesome, Joe. Great work today. Good practice right here. And they are doing a residual plot here to start on this. So we see a regression plot and a residual plot. We see the R squared already turned to a percent for us, usually reported as a decimal. We see I think they're reporting the standard error, S, the standard deviation of Y. It's a little weird right there. That's odd, the way they reported that. They should tell me a little more because it's standard deviation of something, standard deviation of the residuals, probably what they're saying. Intercept is going to be the intercept of the model, which is up here at 78. If you were to plot a line through this, it would hit the intercept at about 78. And then also we see the slope, and the slope is obviously negative because the line goes down. There's a big outlier though. So somewhere up there about 78 is where the line hits the 0 mark. So make sure to understand that that's what that's telling you by 78. And then actually it's positive 78 and then negative 4-ish is the units it goes down each time. So let's take a look what the question asks and use this information. Are the regression conditions met? There is a huge outlier. So QQ straight enough, no outliers, big problem right there. The regression plot shows strong evidence of nonlinearity. No. The regression plot contains clumps. No. The regression plot is reasonably scarred with no evidence of nonlinearity, so it's appropriate. Why are they not mentioning the outlier? They might be mentioning. They're thinking that's a nonlinear trend. A little bit unhappy with that. Doesn't show clumps. The residual plot has much more variation for large predictive values. That's a plot thickening. This is saying plot thickening by saying there's more variation. More variation would be the model getting weaker. So there's not a weakening of the model. I think they're going for nonlinearity with that weird point. That, I do not like the way that's phrased. They should call that an outlier, in my opinion. Is there an outlier? They're not saying the other thing's an issue? Pearson, what are you doing? Yes. Yes, there is an outlier with an X. The outlier has an unusually high life expectancy because when you think about the line we plotted through this, it's way above. So it has an X equal about 2. If you just trace right here, 7.6. I think they give a little bit plus or minus on this. You could probably say 7.5. But if you look to where you're at, its X value is about 7.6 right there. It's a little bit above the halfway mark between 7 and 8. So there is an outlier. Interpret the R squared. 69.5% of the variation in life expectancy is explained by the variation in fertility. In life expectancy is explained by, accounted, they say, for the, oh my gosh, regression. They're calling it a regression model on fertility, which is birth rate. Not my favorite way to explain it right there, but blank percent of the variation Y is explained by the variation in X. Good stuff right there. And is the government leaders, if the government leaders want to increase life expectancies, they should encourage women to have fewer children. No, there's no cause and effect right here. Although there is an association, it seems more likely, no. It does not support the issue. Although there's an association, there's no reason to believe in causality. I'm a little worried about that first question again. Matt Pearson, why are you doing that? The residual plot shows strong evidence of nonlinearity. See, I'm not going to go with that. See, this is where I think they get into the regression problem. Yeah, I knew they were doing that. That's a little bit odd to me that they didn't mention it at the start, that they should have said there's an outlier. They should have said aside from the outlier, because that's not really nonlinearity. One point being far off is not evidence of a linear trend. So I was like, I think they're mentioning the issue right there on that part. This question right here goes into the outlier, which I was like, if they don't mention the outlier, I'm not going to be happy. Because that's a huge outlier in the model there. And you can see it in the residual plot, that huge outlier right there. So they had to mention it. Thank you, Casey, right there. I was a little worried. I was like, there's problems here. And we got to call the problem something. It's not enough for evidence of a nonlinear trend, though. Because a nonlinear trend, now, here's what I'm trying to say to you, is if there were multiple points here, like hypothetically, if you had multiple points up here like this, these wouldn't be outliers. This would be evidence of a nonlinear trend. So with multiple points, we could get evidence of a nonlinear trend, but one point escaping from it is not really evidence of a nonlinearity. One point is just an outlier that does not follow the trend. So you really need more data to go into that idea of nonlinearity. The test will be super clear. Like people will say to me, well, how will it look like on the test? That is a good example of an outlier. Nonlinearity on the test, we actually saw one with the cyclist thing previously, and the model looked kind of like this. So that is a good nonlinear because you can see the bend throughout the model. And you put the linear model in, and it goes woo around it. Animal gestation, yeah. About the R squared super low, what's it mean? Let's do that. Let's do the animal gestation, then the R squared. Probably towards the beginning because they go in a kind of order, like the way they are picked from. Animal gestation. Actually, I think I saw it at the end. Is it not this one? There we go. Animal gestation periods. Okay. Let me mark it in the notes. Animal gestation periods. Stat 201, chapter 8. Is there evidence? Okay, now the number one thing to do is to always mark your what?
Notation, brother.
Number one thing to do when doing a question is always mark your what? Always mark your what? which they've already done this for you to start right here. When you look at that, always mark your what. When doing questions, always mark your what.
Notation, brother.
You should know this, write it down, have them in your notes, review them, become second nature. Always mark your what for 100 points right here. Always mark your what. Always mark it. Every time.
Notation, brother.
You see it, you know it, you love it, you see it, you're going to mark that what? What are you going to mark? I was like, what is it? You want to know? Leo knows.
Notation, brother.
Notation, brother. What do we mean by notation? Well, this is R. When you see R, you should think correlation. R is the value of correlation. They don't say it's correlation right there, but that was what R is. So if you were to remove this point right here, remove humans, then by removing humans in this, correlation would go from this to this. Tighter correlation is stronger correlation. The slope would be like that versus the slope like this. So overall, we get a stronger relationship and we get a higher slope. So with this right here, I have to go to class. Oh, you're welcome. Thank you so much. Check it out later. We'll be doing this. Notation, brother. Thank you, Catalina. Throw you some big points right there. So it would be stronger. Both the slope and correlation would increase. Is there a reasonable justification for removing humans? Sure. Just don't talk about humans. Just be like, let's not talk about humans. Now we see over here this. And we have to know what these mean by constant. And I wish they didn't use the term constant, but it's good to see things differently. It's good to see that every once in a while. So when you go over here to constant, the constant is the intercept. And the slope is the x. So this is b0 and this is b1 and that is x, and marking notation will help right here. We now know we have the intercept value, the slope coefficient, the number of the slope, and we also have the variable name x. So is there an association? Yep, it's pretty strong. Perfect would mean every dot is on the line, and a weak would be more spread out. So this is moderate, strong, pretty good. Interpret the slope, it would be, or the slope, for each 1 unit increase in life expectancy, we expect the gestation period to increase by 12.955 on average. So right there, the gestation period is expected to increase by about, and the slope coefficient, this is the B0. 2 decimals, so we're good on that. Remember, this is B1, excuse me, I said B0. B1 is the coefficient of the slope for each 1 unit increase, and pair that together as like when you do, or now it's just doing predictions. So all we have to do now to make predictions is write the equation of the line. To write the equation of the line is y hat predicted gestation is equal to B0 plus B1x. And we put in here the predicted gestation. Go on screen a little bit here. Predicted gestation is equal to B0, which is 87.5812 plus, and then we go here 12.9550 times x, and then we just plug in 32 for x. And when we plug in 32 for x, we will now solve the number. We'll know what it is. 32. Okay, plus 87 point. There we go. And that is the predicted gestation right there. And it says do not round, then round to 1 decimal. Should be good. There we go. And the r squared being low question, let's go find that one. Oh, low r squared. Low r squared just means we didn't explain much of the variation. I think it's this one right here. Excuse me. So it means our model just didn't do a good job, which is fine. We don't know if this is not statistically significant. That's only measured by p-value. So a student who has created. Okay. So a student who has created a model finds out that their r squared is only 13%. So that would mean 13% of the variation in their y is explained by the variation in their x. So make sure to know that interpretation. R squared is blank percent of the variation y is explained by the variation in x. You will have to fill that out on the test and write it down. You'll have to write down the interpretation. So does this mean that the linear model is not appropriate? No, it has nothing to do with that. My Pearson, are you going to say something like that? Yes, there's no r squared that this is a good answer. This is the answer. That's a good answer. There's no r squared value that must be met in order for a linear model to be valid. Determine whether the linear model is valid involves the context in which the data was collected. Linear model being valid is from QQ straight enough, no outliers, and if the data meets what we would want for a linear model to be fit to it, as in, does it have a straight line relationship? Does it keep to an equal spread? Are there no extreme outliers creating the relationship or destroying it? So the better response would be, as they say, there's no r squared that is like a good value of r squared or must be met value of r squared. But yeah, number 2 on my mind, the accompanying plot. Yeah, let's do that one next. You got it. Thank you, Blakely. So there's no r squared value that needs to be met. There's no r squared, and we see if the linear model is appropriate by checking conditions. And so does the model allow the student to make accurate predictions? A low r squared means we only understand very little of the variation. Scatterplot gestations, yeah, is that, did we not do that one? Was that the one? I thought we just did that one. The scatterplot provided shows the gestation periods and life expectancies of several animal species. But maybe we did a different one. I'll try to find one, Caroline. Thank you, Caroline. Yep, I did one very similar. We'll do that one after the accompanying scatterplot. So this low r squared, you're welcome. A low r squared indicates that there's a large amount of variation around the regression line, which implies the accurate. Yeah, that's kind of right. The model does not allow us to make accurate predictions because the r squared value does not exceed them. There is no minimum. They even said it up here. There's no minimum value. That's wrong. So let's go here, because a low r squared means you're probably not going to make good predictions. You only understand 25% of the variation, but the context matters, because if you have this for the stock market, you're going to get rich. So it should say, well, context is key, but probably no, because they only understand 25% of the variation. But if this is some sort of stock market thing they're doing, understanding 25% of the variation in the stock market would make you rich. So that, once again, goodish answers. The one that said no, it does not meet the minimum, there's no minimum r squared. So that one's obviously wrong. So there's some obviously wrong answers, and then I'll always be like, well, we could improve this answer a little bit. Gallup poll. And justifying the choice. I know the correct model because the r squared is this. No, you should look at your scatter plots to see if your conditions are good. Does the model allow us to make accurate predictions? Yes. Won't fit it everywhere. Always leads. It's a bit of it. I mean, 99.4% of the variation is pretty good, but maybe there's a problem with linearity. Look at your scatter plots. That's the key to that question. We're looking for the accompanying scatter plots. There's the scatter plot provides. There we go. Accompanying scatter plots, and we'll do the one right before this. Okay. And so this is 109, 13, Stat 201, Chapter 8, the accompanying scatter plots. Regression. Okay. First, it wants what is the correlation, and this once again reviews the concept, I believe, that when you go from r squared to correlation, r squared is usually reported as a percent. So looking at this right here, we can turn it back into its decimal format by moving it. And now that is r squared as a decimal. R squared is usually reported as a percent, but it's computed as a decimal. And since this is r squared, we are going to square root it and then check the direction. Since the direction goes up, this is a positive correlation. Once again, we turn the r squared back into its decimal format, where we usually see it before reporting it and multiplying it by 100 to make it a percent to report it. And then we turn it back into correlation by square rooting it. And now we saw it was positive right there. So there's a positive, strong correlation between these, and the 2 decimals right there. The slope and intercept are going to be when x is equal to 0, we expect y to equal to 0 for the intercept. And for the slope, it's going to be for each 1 unit increase in x, we expect y to increase by b1 on average. You will have to write these down for the test, so try writing these down. Rather than reading their explanations, I'm going to write my own down. Here's the intercept. When years since 1950 are equal to 0, when it's 1950, we expect the rate or interest rate to be equal to 0.611 on average. Now the slope. For each additional year since 1950, we expect the interest rate to increase by 0.247 on average, around it to 0.248. Now let's look at their interpretations. On average, interest rate during this period has been increasing by a rate, and this will be the slope. The slope is the increase right there, 0.248 into 2 decimals, so 0.25. starting an interest rate of, and that's the intercept of 0.61. So the value of B1 goes here because that's the increase, the slope, and then the starting value is right there. What would the model predict for the year 2025? What are we gonna have to write? I'm gonna pause right here to see if people know. Let's give it a few seconds. Starts with an E. I'm gonna start writing it out. Help me out. We're gonna have to write our what to solve this. It says 2025. Brian is gonna take a moment and write his what, which we just did for this question too. You're gonna have to start writing your what. You have to know that notation. What are you gonna start writing right here? Help me out, what am I doing? I'm marking my notation right now, and I'm gonna use my notation to write my what. I'm doing it. What am I writing? I'm writing the regression E word. What is the E that I'm looking for? Not residual, it's not the residual. I'm writing the what of the regression. This is the regression equation. That's the regression equation. Y hat equals B0 plus B1X. So we just write the equation, we take the numbers given to us, and then it was years since 1950, and it wants 2025. So 1950 since 2025, which is next year, is 75 years. Take 75, we're off the screen. Take 75 and plug it into X. So all we're doing is plugging 75 into X. That's all we're doing. And we'll zoom out here. 75, plug in. There we go. Compared to all the decimals. There we go. 19.2. And they should see, it should go up to that, and it said 2025, right? Yes, and there it is. And that's a really far extrapolation into the future. So not really. Would you expect it to be accurate? No. That's a really big extrapolation into the future. That should be right. We did it. So really this question was all about write the regression equation and solve it. And then it could ask you like, it was actually this, like we find out in the future, it's actually 18. So what was the residual? So if that's the prediction, it would be lower. So negative 1.2, because if it's actually 18, it'd be below. The question could have follow-ups like find the residual if it was actually 18% in that year. So really good. Just think of follow-up questions like now find the residual or check the conditions. Like think of what these questions are asking you to do and if you can do these steps. Next one right here, the Scatterplot provided. Is this not the one? We can do this one, and I can try to find the other one if this is not the one. Let me know if this is not your question. But y'all's. The Scatterplot. Okay, let's check it out. The Scatterplot provided shows the gestation periods and life expectancies for several animals. The plots contain 2 points that may be concerned. The bottom in the upper right corner of the Scatterplot is the elephants. Let's go find the elephants. That's it tells us that's a good way to visualize. Hey, here's what I want you to see, and there's the hippos. So it's probably going to be asking, what will these points do? And outliers can do anything to correlation. Outliers can do anything to regression. We know that. We love that. So make sure you know that an outlier can drastically increase the slope, decrease the slope, increase R squared, decrease R squared. This is when it comes to correlation and regression. Outliers can do anything. You know I love Lonely Island. So by removing one of these points, we could make the association appear stronger. If you look at this right here, hippos is outside of the relationship, which the linear relationship is here. So removing hippos would make the association stronger since hippos are more of a departure from the pattern. There's a pattern right here that elephants follows and hippos is away from it. Removing hippos would make it stronger. Would the slope of the line increase or decrease? I'm assuming by removing hippos. So hippos is going to have a gravitational pull by existing. Hippos have gravitational pulls. And we look at this and we think, since hippos exist right here, hippos are going to take and pull the line towards it. So by removing hippos, it's going to bring the line back towards the elephants. And I think their answer has a little bit of a weirdness because the hippos is below the regression line. This is true. It's going to increase the slope, but also the full answer is it's below the regression line and it's above the mean of x. So they've had to be very careful right here because if a point were removed down here, then that would cause differences because removing that point would actually decrease the slope. So you have to be very careful. My Pearson really didn't go into enough detail on this one. But the bigger concept, because we don't ask that specific question on the test, like what happened to slope here, and give a very exact answer. The reason that this question is important is it's that outliers can drastically change your regression. Hence, we have a condition QQ straight enough, no outliers, because if you have outliers, it's going to be like the regression line is created from the outliers. We don't want them. We don't want them dictating the line. So I wish they went into more detail because it's above the mean of x and below the regression line. Think about if I have a point here, it's going to pull the line down towards it like this, and then when I release this point from the model is going to go back to where it was. Or if you have a point down here, it's going to pull the model towards it, and then when I release it, the model is going to go back the way it was. So by having this point, it actually makes a higher slope. By having this point, it makes a lower slope. So it depends on where kind of the fulcrum is, the tilting point here, where points down here are going to tilt it this way, and points up here are going to tilt it this way. So the mean of x is an important value dealing with leverage, which is a more advanced concept, but it's just leverage. It's like the idea of leverage right here. Should we just keep animals to increase the strength of the model? No. Should we just remove them? No, don't do that. You can't do that. Only data points that are outliers should be removed. These are such weird answers. I really don't like this question. You don't remove things because they're not similar. All data points from a model should always be kept. No, you can remove data if it's lies. No, only data points should you just keep removing animals to increase the strength of the model. You don't have to even have something that's an outlier to remove it. It just could be a lie. It could be something you know is false. It could be data that follows the trend that is false. So yes, only data points that strengthen the model should be kept. That is very false. You don't keep points to make a stronger model because that's just creating things to have things exist. That's super false. Yes, data points that aren't similar to the mean value should be removed. That's basically saying the same thing, like only keep things to make your model strong, only keep things to make your model strong. Those are super wrong. Only data points that are outliers should be removed. It's really between two of these, and I don't like either of these. It's between B and C. All data points from a model should always be kept. No, you don't always keep all the data points. No one's going to say always keep all your data points. If they do, I'm going to get really unhappy with them. So it's got to be B because you can remove things that are lies. So you have bad data, you remove bad data. So it's got to be B, theoretically. The slope of the scatter plot is 15.5. If you remove elephants from the scatter plot, the slope of the regression line becomes this. It decreases. It's because elephants is pulling it up, and then you remove it because elephants is above here. So you think about where it's at, and then it's pulling it towards it. And then when the point's removed, it kind of releases down. Do you think elephants were influential? Influential means it's pulling on the slope. It changed it a lot. So yes, yes, it lowered the slope significantly. Yeah, this one was just ridiculous. I really want to reach out to my Pearson and be like, that's not a good question. That's only data points that are outliers should be removed. It's like you usually consider removing outliers first, not because they're outliers. You consider removing points because the data is just illogical. We've had people say that they weigh 75 pounds and are 75 inches tall, and you do you, we say here, you do mu, but 75 pounds, I'm 75 inches tall, and I'm not even 175, I'm like 180. So just think about me, 105 pounds less. So it's I don't know, it's like, we just don't think it's possible. And if we're wrong, we're happy to be corrected. So one thing you can do as a researcher is you go back and you look at the data and you go and talk to the person you collected it from, and maybe you find out that it's a real data point and then you keep it in your model. But if you think you have strong enough evidence to believe that the data was miscollected and you can't correct it, you remove it. Now, you're not removing it because it's an outlier, you're removing it because the data is wrong. I can't state that enough. You don't remove data because you don't like it. But you could have data that you find out that the person lied. Like a lot of surveys have what are called a lie scale. And so if you register things on the lie scale, they'll just toss your full data. You get enough on lie scale. Lie scale is often where they ask repeated questions that measure the same thing, and they can tell, like, it might be like, how many days last week did you go out to eat? And you enter in 5. And it's like, how many days last week did you eat at home? You enter 5. And then they say, like, how much money did you spend last week eating out? And you say 5. And they're like, this doesn't make sense. This doesn't make sense. Like, you spend $5 eating out on 5 different trips. I mean, you go to McDonald's and maybe it's true. You go to the person and say, oh, I go to McDonald's and I just get myself a thing off the $1 meal. And that's my weekday meals, my weekday dinner. And then I cook at home 5 nights or 5 lunches a week. So there's ways you could be wrong. But when you make a lie scale well enough, it's like usually try to create contradictory things that a person's gonna, like if they lie, you're gonna see it. And then you could throw the data. And then it doesn't even have to be outliers. You can just be like, I think they lied. If you have good reason to believe they lied, and you're not tossing it because it helps or hurts your model, you're just tossing it because you don't trust the data. Number 1 reason to remove data is bad data. Number 2 reason is probably outliers that you have reason to distrust, good reason to distrust, a logical impossibility of data. So can't toss it because you don't like it. You always have to have a reason for removing data. It has to be a good reason. Gallup poll questions. Yeah, they do that on Gallup polls, Blake. Oh, the Gallup poll question. I was thinking they do that on Gallup poll. Here, we'll do this question, then we'll do the Gallup one next. Interpret the slope in context of the problem. This one's a bit of an interesting one. It catches me off guard sometimes. Then we'll do the Gallup one. The slope is going to be for each 1 unit increase in temperature. We expect the cost to decrease, but look, there's a non-linear to the residual plot. The residual plot is a plot of all the residuals, and you have to know how this was made. If this is the residual plot, then the original regression model, would have looked something. We know the slope is positive. The original regression model would have looked something like this right here. This same sort of bend right here is evident there. So remember, a residual plot is made by making the regression plot flat. It's used to analyze the residuals. You can see the positive residual zone region, the negative, the positive, the positive, the negative, the positive, where it's about at 0-ish, especially that point right there. So know how a residual plot is made, called diagnostic, to diagnose the regression, like my cough. No. Okay. Interpret the slope in context. The model predicts a 2.4. Oh, it's decreased. Uh-oh. So the line should have gone down. Can't have a bad drawing on here. Can't do it. All you do is you just draw the same relationship in the residual plot around a line that goes downward. There you go. And then they got that point right there. So that is the same relationship, but now on a downward slope. So, and we're predicting the cost. So it's going to be a decrease in heating cost right there. And it's by the quantity of B1, which is with the X right there. Next, we have interpret the y-intercept. And this is would be when the average temperature is 0. The model predicts a heating cost of 150 when the temperature is 0. That is the value of B0. During the months where the temperature stays around 32 degrees, would you expect the costs on the model to be accurate, too low, or too high? So 32 is right in here. If you notice, the predictions to me, and this always gets, I fear this is one that gets me, is the model is predicting too low because the points are below. So we're going to go with that here. Too low. Uh-oh. See, look, too low because the residual is positive. That doesn't make sense. Too high because the residual is negative. I think they changed this up because if it's too low, the residual would have to be negative. So they're actually telling us what the answer is here, because if something is predicting, what did it say here? Would you expect the cost predictions based on the model? Oh, no, it's right. It's right. So it'd actually be too high because the residual is negative. And what I'm saying right here, let me show you visually, is when you go to 32, almost tricked myself. When you go to 32, 32 is right here. And if you look at the model's predictions, the predictions are too high because the actuals are lower, making the residual E negative because it's below the prediction line. So I expect the predictions to be too high because the residuals are negative. When heating cost does the model predict for 10 degrees, go right here to the model and enter in the values. It's going to be about beep, 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 beep. Computer 128.6. Let's see if I got it right. I do it in my head. 10 times 2.14, 150 minus. There we go. We did it. Just plug in 10 for temperature and then solve the equation to get the predicted value. During one of the months on which the model is based, the average temperature was 10 degrees. What were the actual heating costs? So right here, you can see the prediction would have been 128. So actually, let's draw that because we have a picture up of this. So the value, and this is the prediction we got. Remember, that's the prediction. Oh my gosh. So the prediction for this is 128.6. Now, what you'll notice here is we can see the residual, and the residual E looks to be about -3, which means the actual is 3 below. So we just subtract 3 from it, and we get the actual of 125.6, and that's the actual value. And this is a pretty good question right here, especially when you look at the methodology for it. Because remember, this is the prediction line. This is your regression line. It's just your regression line that's been made flat. So this is the regression line. As in, when you look at this visualization I have over here, this right here is what I just highlighted, and it's this line right there. So they're having us use the line in a residual plot to do the calculations, and we can then see it. Remember, it's still just your regression line. It's just been made flat. So the residual of -3 tells us that the actual is 3 below the prediction. So we just subtract 3 from the prediction to get the value. So since I estimate the residual to be -3, if you look over here on the left, I'm going to subtract 3 from the predicted value. And we got the predicted value from the last equation. So that's 125.6. That's a really good question. So until I get it wrong, then I'll say it's a horrible question. Round to the nearest dollar. Oh my gosh. Did this one say round to the nearest dollar? Round to the nearest cent. I want to watch you round to the nearest dollar. That's mean. Do you think the homeowner should use this model? I'm going to get really mad because I'm going to say no here because there's non-linearity. So my issue is no, there is non-linearity, and we'll see what they say about this, but I'm saying it's a non-linear model, got problems. Would this model be more successful if it was created using Celsius? No, the units don't matter for this. The units not influence an accuracy of a regression model because regression it's kind of based on z-scores too. You get z-scored, it doesn't matter.
It doesn't matter.
Do we get them all right or one wrong? 100%. I like that right there. That one had me worried. I wish they went into more detail on why should you not use this model. It's due to the bend in the model. The model clearly has a non-linear nature to it, and that is a problem with QQ. Straight enough, it's not straight enough. So there's a huge problem with this model. They should have gone into that. A lot of good calculations when it came to the residuals and the actuals and understanding those relationships and seeing a residual plot. But you really have to understand that the residual plot is a diagnostic plot created from your regression plot. So those are some key understandings right there that we should have that I hope you haven't missed. The Gallup poll question should be nice and fun right here. Let's do the Gallup poll question. The Gallup poll question. Step to a wall. The Gallup poll. I might get a lot of this done. Okay, the Gallup poll has tracked cigarette smoking in the United States since World War II. And if you look, this is the model's pretty good. Now, what I wish we'd talk about in this class is there's really cool advanced stuff. If you're in 207, you know I love talking about advanced regression models. This model is generally pretty good, except for the start. So we actually have something called piecewise regression, where you fit a regression model here and you fit a regression model there. You do it in pieces. So because there's a linear trend from about 1975 going forward, and then there's really no relationship at the start. It's kind of a random scatter. And so we have a negative linear trend afterwards, and the question is probably going to get into that. Is there a clear pattern? Yeah, we talked about it. So the adults who are smoked between the 1950s, the trend has become nonlinear since then. No. The percent of adults who are smokers decreased non-linearly. No. The percent of adults who were smokers did not change much until 1970, where the numbers of smokers started to decrease dramatically and linearly. That makes sense. Is there an association? Yes. The association appears stronger. No. The association appears weaker before the 1970s until after. Yeah, about there. Yeah, sure, 1970s. It depends. I don't know. Somewhere in here, it starts to change. So it appears weaker before the 1970s than after. Is the linear model appropriate? No, a linear model would not be appropriate throughout, although one could fit a linear model going beyond, kind of going into piecewise regression. So there is a linear relationship. I was zoomed in on that, but I think you saw most of the answers. There is a linear relationship beyond 1970, so we could probably use it. You might just have to limit the scope and say that the linear model is pretty accurate for these years, but there's a nonlinear relationship at the start, so you could limit the scope of your x's. And not the worst idea. Piecewise regression net. Not a bad idea. I think there's any other big ones. A lot of these. Let's do a few more. How's everyone doing? Blakely, doing well? We're gonna do a few more here. Grab a snack. Back to a 1, chapter 8 quiz. Okay, concert production. Concert production company manages its records. The manager made the following scatterplot. The company places concerts at 2 venues, a smaller one and a larger one. I got this one wrong the previous day. Not happy about that. You notice the larger one has more variation around the line, where the smaller one would have less. What I'm saying right here is if we fit the linear model to these, we could see that the blue one is tighter around it and the red one is more spread out. Also, the red one has a larger range of x values. So let's see, describe the relationship right here. Both are positive. So both are strong, positive, linear, and that does it. Strong-ish, yeah, and there's one outlier that stands apart from the majority of the data. Yeah, there it is right there. Yeah, because that could be above the line. Yeah, one outlier. How are the results of the 2 venues similar? Both show an increase right here, as in there's a positive relationship. They both go up. How are they different? The larger venue has greater variability, making it harder to predict. So, and by variability, they're talking about variability. Concert production is the one I have. Yep. Is this the one right here? We just did it. So this is the concert. Is there another concert production one? By more variability, they're talking about the smaller one has less variability and the larger one has more variability right here. This is the larger one's variability, so that's harder to predict. Is it a different one? The smaller one is tighter, making it easier to predict, better R squared. The larger one is more spread out, probably lower R squared, excuse me, making it harder to predict. So that's got the concert production. That is the concert production one. Here's another concert production one. We'll do the second concert production one. So a concert production company examined its records. The manager made the following scatterplots, and let's look at them. Same sort of deal, except this time they're more separated. And so looking at these scatter plots, we want to immediately fit some lines to them. And by fitting the lines to these, you can see a line here and a line here. Now they're very similar, except the larger venue has a larger range of x's, where the smaller one has a smaller range of x's. The larger venue is once again more spread out, and the smaller venue is a little bit tighter right here with its relationship, making it a stronger relationship. So the larger venue, they both have about the same positive linear relationship. The larger venue has a greater range of x values. It goes across, having more ticket sales going from the lower to higher values. And it's clear to me that they kind of switch to a larger venue when they exceed certain ticket sales if they're a production company. So does the relationship describe it? It is strong positive. There are no outliers. Everything seems to follow the trend. No clear outliers like the previous one. How are the results of the 2 venues similar? They both show an increase in revenue with ticket sales. And how are they different? The larger venue, yeah, so they're saying there's just a wider spread of the X's. The way they word that is just weird. They should just say that the larger venue has a greater variability in the X's, or they say when they're talking about the magnitude, they're talking about there's more spread to the values of ticket sales for the larger venue. Oh, it's a weird way of saying it that they say it. The larger venue populates a higher magnitude of the plot than the smaller magnitude region of the. No, they should They should just say there's a greater spread on the X. There's more variability in the ticket sales. Okay. Regression line. We'll do the constant production one here. Okay, management is considering adding a stadium that would seat 10,000 people. What does the model predict the revenue would be? We're just going to go here to ticket sales. And on the ticket sales, we're going to enter in 10,000. And we'll do the predicted ticket sale, the predicted revenue. So now be careful. Ooh, something happened here. Something. Remove that. Maybe that was right. No, that's not right. There we go. And then you need to subtract from it 13. So make sure you do the math correctly to get the prediction right here. Double check your work. All we did was plug in 10,000 ticket sales to predict the revenue. Now let's take a look at the model and ooh. What have we done here by going outside the bounds of our X's? What have we done here by going outside the bounds of our X's? X's. Does anyone know for 100 points in the chat? Our X's only go to about 32,000 or something like that. So 3,200. So we have predicted all the way out here beyond our X's. We have what? We have whatted. Horrible handwriting. We've done an extrapolation, which is predicting outside the bounds of your X's. So with extrapolation right there, we can't really rely on this prediction because we don't have data there. So, and they don't even say, an extrapolation as far would not be reliable. Yeah, that's the answer. I thought they weren't going to say the word extrapolation, but that's a huge extrapolation, predicting well beyond the bounds of your model. Oh, another concert production one. Oh my gosh. Concert production company offers advanced sales to frequent buyers through its website. The Accompanying Scatterplot shows evidence, sales venues and revenues, advanced revenues. Oh yeah, that's it's got some non-linearity to it. So you always want to try to fit the line through your data. And it goes kind of like this. So that is a non-linear, if you ask me. The point, what? Okay. Why would it be unwise to assume that the model accurately predicts the venue in this situation? Okay, and they want to do what? A performer who refuses to permit advanced sales would like to predict their revenue using the model. Oh, so their advanced sales would be 0. If a performer won't do advanced sales would be 0. And you say, well, just take the model and extend it out here. This is the same idea that you have extrapolated your model. Extrapolated. So this is a bad idea. You're extrapolating your model again where you don't have data. So the point is far from the other ones used for the model for total revenue, because that's what we're trying to predict. Therefore, an extrapolation of this far is not valid. There, extrapolation, yeah, should be right. Yeah. So we're trying to predict total revenue, and this is a bad idea because we're very far away. Did all those. Let's finish this off right here. We'll finish it off. 39, 13. I think I only missed one today, and I misread the question. So the correlation between cell phones. The correlation between cell phone usage and life expectancy is very high. Should we buy cell phones to help people live longer? No, as I disappear right here. This is the idea of a lurking variable right here. It probably has to do with wealth. A lurking variable is a variable outside the XY relationship. We saw some classic examples yesterday. I don't have the notes still open. But with yesterday, we talked about shark attacks and ice cream sales, X and Y. The lurking variable would be things like summertime or the weather outside, because you're more likely to go outside and eat ice cream when it's hot. You're more likely to get attacked by a shark when you're in the water and it's hot. So we should say no right here. And that just looks, oh wait, and for people who are relatively wealthy, and those who are typically wealthy have longer life expectancies. So there's a lurking variable in the model. Should just look for a lurking variable. Lurking variable is a variable outside the XY relationship, like shark attacks, ice cream sales. Summer's the lurking variable. Cell phones, life expectancy, wealth is a lurking variable. You have wealth, you buy cell phones, you have wealth, you live longer. Not saying you will, but there's a relationship. It's summertime, ice cream. Summertime, sharks. So it's sharks and ice cream look like they're connected because they're connected to a lurking variable between them. So that is how lurking variables work. A variable that is not part of the model but affects the variables in the model is called a lurking variable. The explanatory variable is the X and the response variable is the Y, but something outside the model like summertime with shark attacks and ice cream sales. Summertime is the lurking variable. Here we go. We only got 2 more. We'll done the full quiz. Let's see right here. And let's mark these. We've done the full quiz. Oh my gosh, I started a tiny bit late today. Got the lights going. Doing the full quiz? Is there evidence? Okay. Is there evidence that the age at which women get married has changed over the past 100 years? The Accompanying Scatterplot shows the trend in the age. Let's take a look, and what do we think? Oh yeah, it's changed. Kind of dipped in the 60s and then has been increasing, so it's non-linear. Important thing to think about is, should we fit a linear model to this? The answer is no. Even there's a bit of non-linearity here. You're welcome, Blakely. Thank you for being here. 100 points. We're going to finish off this quiz, do all the questions. Is there a clear pattern? Yeah, there's a pattern. So the trends appear to be non-linear. So that's basically does it for me. Yes, there's a trend, and yes, it's non-linear. There was less data collected in this region. That's why there's gaps. They didn't collect every year. Is the association strong? For strength, it's tightness of the relationship. Good to see you here, Davis. So we want to look how tight this relationship is. If it is tight around the form, put it this way, the form is this, and the tightness is super duper 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 tight. It doesn't have to be linear to be strong. It has to be tight, as in compact around the form. And since it's so tight, compact around the form, that is super duper strong. It's not linearly strong because it doesn't follow lines so perfectly. It's super duper strong. Is the correlation high? Yeah. It does have some correlation, but the whole graph is non-linear, so I don't think, and we should not fit a linear model. No, a linear model would not be appropriate, although one could fit it for the later years. I was a little worried about that correlation one, because you'd be shocked at what has good correlation, and even things that have non-linear patterns have some correlation. So the last one was, should we do correlation or linearity to this? No. Because it doesn't have a linear pattern that is seen throughout the data. My guess is correlation is probably going to be, like, if I had to tell you the correlation of this, I wish they gave us the data, probably going to be about this. Now this portion has a correlation of like that or something, but the beginning part is destroying it, like 0.98 for the really strong parts. So, an analyst, we're on the last question. Oh my gosh, we'll have done all the questions. Oh my. Okay, swing by office hours anytime. We can go to depth on any questions. This is the last one, an analyst. Try to figure out the regression model here to each segment of a data set to test a model. They made the model predicted January is equal to $612.07 plus 0.403 cents times December. What does this say about the analyst's concern about the model? Were they justified in worrying about the overall model? Might not be accurate. What does that say? The model? What? Okay. So what they have right here is a mess. No one should ever make a graphic that looks like this. And each of these, so they're testing the January model. Oh, and they have segments of a data. So that's really weird. They shouldn't even talk about that here. They just have different, and they're talking about the red line right here. So there's ones with negative relationships. So the red line, that does look to be the pot. It might be the red line. Should have said that. But the rest of the data doesn't follow this trend. It's a horrible idea. They didn't do random segments or something. This is a weird question. No, each segment has a different line of best fit, so they follow different relationships. What? Oh wait, what does it say? Were they justified in being worried? I thought it was, should they do it? Yes, they were justified in being worried. Each segment has a different line of best fit, so they follow different relationships. Yeah, there we go. I thought it was, should they do this? No, they shouldn't do this. But yes, they're justified in being worried. So I don't like that. When I see the answer, it's the linear relationship is not constant between the segments of the data. They shouldn't fit it to the overall data. It's really good stuff. I'm gonna go grab some food. We're basically done on time. Till then, bye for now, everyone. Bye.